let's use the idea that the derivative of a function is 0 when the function is changing its value from decreasing to increasing. And we're going to call that the first derivative test and use it to find extrema, minima, maxima, and intervals of increase or decrease on the function. So to lead into this, what does the first derivative actually tell us? Well, we know that the first derivative of a function tells us the rate of change of that function at any point. How is the function changing throughout the function? And we can see intuitively that this green function here, f of x equals negative, the quantity x minus 2 squared plus 3, is increasing, then it's constant at x equals 2, and then it's decreasing for the remainder of the function. So if we were to take the derivative throughout, we would find where the derivative is greater than 0, the function is always increasing. And this is true of any function. We'd also find that wherever the derivative is less than 0, the function is decreasing. And finally, and perhaps most importantly, we find that where the derivative is 0 represents where the function is constant. So if the first derivative can tell us a lot about the function, whether it's increasing, decreasing, or constant, let's see how we use that first derivative in a step-by-step way. First, we're going to take that derivative of the function, so we're going to take f prime of x and set it equal to 0 because interestingly enough, it's where the function is constant that represents where it changes from increasing to decreasing or vice versa. So step 1, take the derivative, set it equal to 0. Step 2, find out what values of x, what input values actually make that derivative 0. Those are the points where the function is constant, and again, they represent transition points. These are the boundaries from increasing to decreasing or decreasing to increasing. Once you've found those boundaries, those places where the derivative is 0 and constant, then make a table. And that table should have, of course, f of x, and f prime of x. And you're going to choose values of x that are on either side of all the places where the derivative is equal to 0. So for example, let's just take this hypothetical function where the derivative is 0 at x equals 0 and the derivative is 0 at x equals 2. Not only are we going to use those values, but we're going to use values of x on either side of those, and that's going to give you the entire picture of what's happening on the function. And so what you're going to do is test the derivative at all those points. Test the first derivative. And if we're choosing one value on either side of the points where the derivative is equal to 0, we get an entire picture for the function. So we chose x equals negative 1 because it's on the left-hand side of one place where the derivative is 0. The derivative happens to be positive at that point. So we put kind of an upward-facing arrow to show the function's increasing. At 0, we know the function is constant. At x equals 1, we take the derivative and find it to be negative. So we know at that value of x, the function is decreasing. At x equals 2, that's another point where the function is constant. The derivative is 0. And then just beyond 2, we picked x equals 3. The slope is positive. So in the end, we took that function, we made the table, and looked at the derivative at points on either side of the numbers, the critical numbers where the derivative is 0. And we used it to determine all the intervals on the function where it's increasing, decreasing, or constant. And that's the essence of what the first derivative tells us. It actually gives us the intervals over which the function must increase, remain constant, or decrease. So let's take the first derivative test and use it to analyze the function graphed here. F of x equals negative, quantity x minus 2 squared plus 3. So first thing we'll do is take that first derivative. F prime of x then, using the chain rule and the power rule, would be negative 2 times the quantity x minus 2 to the first power times the derivative of what's inside, 1. Of course, the derivative of 3 is 0. So we've got to set that equal to 0. So where is this derivative equal to 0? Because we know that's going to be where the function is constant. It's going to be a transition point between increasing to decreasing or decreasing to increasing, as the case may be. So we're going to set that derivative equal to 0. So 0 equals negative 2 times the quantity x minus 2. We divide by negative 2, we get 0 equals x minus 2, then add 2 to both sides, and so the derivative is equal to 0 at the point where x equals 2. That's the only point on this function where this occurs. It's the only point where the function is constant. Let's make a table. And we've got to choose some values of x here. That's the first step. So values of x that we want to choose at x equals 2, of course, and then we want to choose values on either side of that because we know the function's constant here. We're going to pick values of x on the left side and the right side of that. I chose 0 and 3 because they will help. I can solve them easily. It does not matter as long as you pick values on both sides. So if we know those are the x values, what we're going to do now is find the f of x, the y values that correspond with those of the original function. And when you evaluate the functions at 0, 2, and 3, you get -1, 3, and 2 respectively. What's the derivative at those points? For the first derivative test, the actual value of the first derivative is important. What's important is the sign, S-I-G-N, sign, positive or negative, of the first derivative. And if we look at the point where x equals 0 and we put it into the first derivative, we get -2 times -2, which is positive number, positive 4. So therefore, over that interval on the left-hand side, the derivative is positive. At the point where x equals 2, we put in a 2 for x into the first derivative, and we get -2 times 0. And then on the other side, we're going to put in x equals 3, so we get -2 times 1, which is a negative number, meaning that the slope is negative beyond this transition point. So then we draw some arrows to indicate visually what the function is doing. It's increasing all the way up to x equals 2, then it's constant for that instant, and then it's decreasing the rest of the way. The function cannot do anything else because of the first derivative test. What that also means, when we see this pattern of increasing, then constant, then decreasing, like we see in this function, that means the critical number here, the extreme value at x equals 2, is indeed a maximum. So the point x equals 2, y equals 3 is a maximum on that function because it's increasing, then constant, then decreasing. And as you might imagine, didn't happen in this function, but it could in other functions. If you had a decreasing, then constant, then increasing, that represents a minimum. So these arrows can be very helpful in getting a picture of what's happening on the function. If it's increasing, constant, then decreasing, the point that's in the middle is a maximum. If it's decreasing, constant, then increasing, that point happens to be a minimum. So let's take the function you see here. F of x equals x to the third power minus 6x to the second power plus 9x plus 2. We're going to use the first derivative test to figure out what's going on with this function. First, we're going to take the first derivative, 3x squared minus 12x plus 9. We're going to take that first derivative and set it equal to 0. Looking at this, I can see that there are factors of 3 in all of those. So if we divide the left and the right sides by 3, we get this quadratic function here, which is indeed factorable. When we factor that, x squared minus 4x plus 3 equals 0, we get 0 equals x minus 3 times x minus 1, which lets us know that the factors of this are 3 and 1, x equals 3 and x equals 1, which means those are critical numbers. That's where the first derivative test results in 0. So what values of x do I choose? Well, I'm going to choose 1 and 3 for my table, but then I also have to pick numbers to the left and right of 1 and to the left and right of 3. So in this function, 0, 1, 2, 3, and 4 work very nicely because they include all the intervals to the left, right, in between 1 and 3. So we evaluate the function at those points, and we get the values you see here. Then we evaluate the derivative at those points. Of course, we know the derivative is already 0 at 1 and 3, so let's look at 0. And if we put in a 0 into this function, this first derivative function, we get -3 times -1, positive number. If we put in a 2, we get -1 times positive 1, which is a negative number. And then if we put in x equals 4, we get 1 times 3, a positive number. So we now know the pattern the first derivative has on this function. It's increasing, it's constant, it's decreasing, constant, then increasing again. And if we draw those arrows to help us picture what's going on here, that gives us a good view of what's going on in this function. And since we see this pattern increasing, constant, decreasing, we know at this point right here, 1, 6, we have a local maximum. Since we also see this pattern decreasing, constant, increasing, at this point 3, 2, we know that point is a local minimum. And indeed, when we graph this function, we're going to see that it confirms what the first derivative test tells us. The function is increasing all the way up to the point where x equals 1, where it is for that moment has a slope of 0, and a maximum, then it decreases all the way to x equals 3, where it becomes a local minimum, and then for the rest of eternity, that function increases. All of this information comes to us from the first derivative test. So use that first derivative test to find out pretty much everything that's going on with a function in terms of whether it's increasing, decreasing, or constant, and all the intervals where that happens.